Okay, so let's see. Welcome back, and we were seems to come back up again. Right. So we were discussing about structure in the last class before the break, and the discussion was actually focused on kind of probing techniques. How do we look into the crystalline or the amorphous nature of solids or liquids or gases for that matter? And what we discussed in the last class was essentially we are going to bounce off some sort of particles, be it photons or electrons or neutrons, right, from the solid, and we are going to look at what's at the reflection or the transmission, and from there we can figure out what's the arrangement of atoms inside the solid, right? That's the basic idea, and and I kind of tried to stress in the last class was this idea is actually a very general idea, and every so in general this sort of experiment would be called a scattering experiment. You know, you're essentially scattering stuff off a solid or any object, and you're looking at a reflection and looking at and from there reconstructing what that object really is, right? So, and when we see something, and we are doing exactly the same thing. You know, light is scattering off objects, and your brain can figure out what the object is. Okay, so we tried to put that down into a mathematically rigorous form, and then that's why we ended up in the last class with what we call as the structure factor, right? That's what we derived in the last class, and I'll kind of start from there today and start. So today what I'm going to do is look at the structure factor, point out a few very basic things you can get out of any such scattering experiment. You can conclude quite a few things by looking at the whatever has been reflected or transmitted from this structure factor pattern. In fact, when I say you can conclude quite a few things, the more accurate things, you can conclude pretty much everything you need to know, because as you remember, the way we started this problem was we said that, well, we'll have a set of point scatterers, be it atoms or molecules or anything of that sort, that are distributed in real space, right? And the location of each of these is we label them with a vector, say rj and rk and so on, right? So all these particles will have a location vector, and then we are now scattering off electrons or neutrons or photons in an X-ray format or other formats, and looking at the screen out here, right? And whatever patterns develop here, we're looking at that now, right? And the equation for whatever pattern that develops there, if you remember, the way we kind of, just as a quick summary, the way we ended up there was we said that let the scattering strength of each of these atoms, I think when I say atom, we understand it's a general term, that there's a certain function associated with it. Could be due to the electron cloud, could be its mechanical properties when you're doing neutron scattering, you know, the mass density or things like that, right? So it could be any of those things. But essentially we said that whatever be it, I'm going to just absorb all that information into a function attached to every point scatterer, right? And from there I create, from a point scatterer, I create a field which essentially has the information of every point scatterer, and in addition to the information about every point scatterer individually, it also has the information of how they're located in space. Are they periodic? Are they completely amorphous, disordered? What sort of the polycrystalline? So this field now has everything, right? And so, and when we say that when we are taking an experiment like this, when you're doing an experiment like this, you have waves incident on it with the incident wave vector q, which is basically 2 pi over the wavelength of incidence in magnitude, right? And then you have a reflected Q out, let's say, right? And it has, again, 2 pi by wavelength out. And then we're looking at this. So essentially, what we are, so the particle or the wave actually scatters, and then there is a difference between the incident and the reflected geometry, right? So essentially, if I label the difference as Q incident minus Q out, right? That's the Q vector. That okay, so this is the difference. And when I stated in the last class that what you see on the screen is a Fourier transform of this field. That's what you see. And when we take the Fourier transform, we get phi of Q. I think sometimes there'll be a tilde or things like that just to be accurate, because you know the function here. Maybe you can put a tilde saying it's a Fourier domain in of this. So essentially, essentially what we're doing here is, if you are in 3 dimensions or any dimensions, you can Q dot R, and then you plop that in here. J F of R minus RJ, right? So that's what we were really after in the last class. And what is this Q? It is exactly this difference, that's what it is. But the angle of deflection in some sense, or not the angle, but the wave vector of deflection. And that's really what it is here. So, and from here, what we realized is, if I know the Fourier transform of one function, meaning any one of those atoms, let's say its Fourier is that, then this thing is actually just a shifted sum of each one of them, right? And what we found was this is, you can pull out the f of q, just do a change of variables here, r minus rj or something like that, and what we end up here is u q dot I q dot rj, right? Over all j's. That's what you end up with, really, right? So so this is the total field in the Fourier space. And what we are observing here in the screen is really not this, but it's mod squared, the absolute square. We are counting the number of neutrons, number of electrons, number of photons. And the number, I think we know from, if you think about classical electromagnetic theory, the intensity of light is not the electric field, but square of the electric field, right? And in the same way, in quantum mechanics, the intensity or the number of particles is not the amplitude of the wave function, but the mod square of it, right? So as a result, what you're really measuring is intensity as a function of q, and that is phi of q whole squared, and that essentially becomes f of q whole squared times, you see there's a sum of these quantities, and the way we wrote it in the last class was e to the power I q dot rj. And when we say square, we these are complex numbers, so it's number times its complex conjugate, right? That's psi star, or so we get a j here, and the second one will be complex conjugate of I e to the power I is e to the minus I q dot. So I write a dummy index here with a k, so k, right? So that's the total field or the total intensity after scattering events. Any questions here, or this is hopefully you've encountered it in many courses, not just one, because it's very standard stuff for many scattering techniques. And what we did now was we said, let's say I have n atoms here, n atoms, big N. It could be very large, could be 10 to the power 23 or 10 to the power 25, or it could be 5. Right? You could have a cluster of just 5 atoms. It could be anything, or it could be 1. So what we're going to do is kind of normalize this now, and the way we're doing that is multiply this prefactor by n and divide this whole thing by n. All right. So we just normalize it, and we'll see now why we are doing it, because then you'll get a structure factor which can be of the order 1, for example. Okay, so that's and this whole quantity out here is what is referred to as the structure factor. That's what. So this is labeled as S of q. And that quantity here is the structure factor. And as you can see, the structure factor really does not care about the nature of atoms. That's here. Right? It only cares about the geometry in which they are arranged. Right? That's what it really cares about. Right? And the geometrical relation is their periodicity, or is it amorphous? But it doesn't care about the nature of that. The nature of the atoms is all here. Is that clear? So that you split it into 2 now. And now we look at the structure factor a little bit more in a little bit more detail, and try to pull out some information from it. Okay? So and see how will it look if I had a crystalline solid or not, and things like that. Okay. So the intensity is equal to this and that. And just before I go ahead, I'll point out that some things that you may have taken courses and seen is for example, if I have let's say I have silicon. This is not so. Let's say I have silicon and I have silicon carbide. In silicon, all the atoms are silicon. In silicon carbide, half of the atoms are silicon, half are carbon. Right. So that information actually shows up not here but here, right? Or in gallium arsenide, for example, or gallium and arsenic. So that changes this factor, right? But not that. Meaning if the lattice constants are the same. So for example, in silicon, there will be some peaks that may be missing compared to gallium arsenide just because there are two atoms. There's a broken symmetry there as well. So this will have some extra peaks, extra spots, for example. So that maybe if you have had a course on from solid state or normal crystallography, you know that part of it. Okay. So we're going to now look at this one a little bit more detail. And write that the geometric factor, the structure factor here is this whole big sum, and I think it's clear the way the sum looks. So I'm going to just write it out in terms of. All right, let's actually write it. I'll rewrite it again. Okay. Rj e to the power I q dot rk, right? Whole thing divided by n. So let's just look at it a little bit carefully and say how many terms are there in the numerator? So how many total? If I were to expand, write it all out, how many terms are there? Right? Sorry, yeah. JK, yeah, but remember the J. You're right, but J is going from. We are running over all the atoms. There are n atoms. Or n sides, so we're running over all of them, right? The sum runs over all, right? So as a result, so this has n, right? And that also has n different terms. So you have n squared, right? You have n squared terms in the numerator, right? And the denominator you have exactly equal to n, right? So what you can do is you also realize that, sorry, I missed the negative sign here, so it's complex conjugate, right? And you realize also that the j and k are dummy symbols. What does that mean? It means for every j here, let's say I'm looking at R5, there's also R5 here in one of the sums, right? And it has a negative sign, right? So they all such similar products give you 1 each. Is that clear? So each of them is giving you 1. So what you actually have in the numerator then is, if I were to expand the whole thing out, you have basically n, because there are 1 plus 1 plus 1, and there those terms, plus a sum that looks like this, e to the power I q dot product rj minus rk, where now j is not equal to k, right? That's how it looks, right, in the numerator. It's just, very simple, really. Keeping track of what we have in there. And so the whole thing now divided by big N, but now I hope you see the reason for this normalization, because now what it becomes is this is just becomes 1, right, plus 1 over n. So, right, and how many terms are here? Again, now that is basically clearly n square minus n terms, right? Because we took out the first n there, so that's how many terms are there in this cross product term, right? Sum of the cross products, right? N square minus n terms, and so you can then write, okay, so this is basically another way of writing the structure factor, which actually has maybe a little more physical feel to it. Is that clear? So, did I do this right? Yeah, I think so, right? So there are n terms, 1 plus 1, and then there are n square minus n terms, right? Okay, so now you see that what you have here is on the right side, or this term, is really a sum over complex exponentials, right? E to the power I thetas, right? These are basically e to the power I theta terms, right? And e to the power I theta, if you look at real part of, let's call that this whole thing as every term has, let's call it a complex number z, and we know that it lies on the unit circle, right, in the complex plane, where this is real part of z and this is imaginary part of z, right, and all these points are sitting on that circle, right? That much we know for sure, right? And at this point we can start looking at what will happen if the arrangement of atoms is perfectly periodic, or if it's not, and things like that. This is where we can make that. So let's say the arrangement of atoms is completely random and it's an amorphous material. That's the definition, when there's no correlation between any two atoms. That's the meaning of random or amorphous material, right? No correlation between finding an atom here and moving 4 angstroms or 5 angstroms out and finding another one there. There's no correlation at all. You may or may not find it. The probability is undefined in some sense. Okay, so in that case, clearly what it looks like that this term here is, or rather the phase, the theta, which is q dot that thing, is going to be randomly located on the circle, right? They'll be located all around, not necessarily, but it will be completely random, and I think you can see very clearly why they will add to 0. Right? Do you see that? I mean, they'll have equal and opposite real and imaginary parts, so there will be, because of the randomness, you can see it will basically go to a very small value asymptotically, right? Because you are adding, a certain number of real parts, a certain number of positive real parts, negative real parts, positive imaginary parts, negative. So all the sum to 0. Do you see that? I mean, is that at least makes plausible sense, at least, yeah? So they add to 0, and as a result, the structure factor is 1. It's just 1. What does that mean? It means there's a haze here. There is no pattern at all. Everything is the same. Right? Does that make sense? So the screen you see, there is no dependence on Q at all, right? There's no, so this appears as isotropic, so you get just a haze. So that would be the case for an amorphous solid, right? Or any questions here? And you can try to simulate it. You use MATLAB Mathematica and take this up, generate a random number for the phase, and calculate it. You'll get it. Basically, this will add up to 0. Now, let's look at what would happen if it's not random. I mean, obviously, that's really what we're interested in, right? Now, if it was perfectly ordered, it's a perfect crystal, then again, we know that this quantity, Rj minus Rk, right? What do we know about that? The vector separating two atoms is always equal to, rather, if we take Rj minus Rk, right? So if we take mod square of that we know that it's some integer times a naught square, where a naught is the lattice constant, right? That we know, right? Because they are all real space lattice vectors and such things. But I think from here also you can see that the reason why we define the reciprocal space of Q, every time the argument becomes 1, the argument becomes an integer times 2 pi, right? So these all become 1. Every one of the n square minus n terms becomes exactly equal to 1, right? What does that mean? It means if Q dot Rj minus Rk is equal to 2 times some integer times 2 pi times an integer, right? N is an integer. Then e to the power I 2 pi times an integer. You're not going around the circle anymore. You're sitting right here, right? It's at 1 comma 0. All of those n square minus n terms are equal to 1. And therefore, what you get, if you go back again, you get n square minus n plus n. So actually what you get is n square by n, right? And you get the structure factor becomes equal to n, the number of atoms, right? If it's perfect. And this happens only when Q is equal to that. So that means you have to have a particular wavelength and maybe an angle of incidence also of the electron or the neutron or whatever, right? You're bouncing off here. So that must be precisely equal to. And that's I think this is the defining relation also for what are those Qs? Well, Qs then for this to be satisfied, the Q's must be equal to the reciprocal lattice vectors b2 comma b3 times any integer, right? You know that part, right? It's some linear combination of these reciprocal lattice vectors where b1 is 2 pi a2 cross a3 over the triple product. I think we have done that, right? So a2 a2 a3, right? These are the reciprocal lattice vectors, which I think there's a 2 pi missing in the textbook for whatever reason, but I think you know what I mean here. Okay, so yeah, okay. So what does this mean? All it means is for certain Q's now for this solid, you have bright spots, and these spots are separated. These spots form in Q space. They form a lattice too, and this is the reciprocal lattice. Right? They also form a periodic lattice, and the periodicity is these are the lattice vectors in the reciprocal space. And the structure factor really becomes equal to the number of atoms. So that means the more the number of atoms you have, the bigger the solid, the higher the number of, meaning more intense the peak. Does that make sense? Okay. Yeah. We can say actually a little bit more. Now what we can say is, what if we had a finite number? Or rather, how does it depend on the number of atoms? Okay. So what we could do is take up a very simple situation of, instead of a 3D, we can take just a 1D lattice and see how will it look. So we can take just a 1D, one-dimensional lattice of these atoms, and this is just for analytical evaluation. I think can do it for 3-dimension really, but the structure factor for basically scattering off here will be from, you can actually kind of just go here. If you have periodic lattice, you don't have to make all these things. This is just to show that if you have amorphous solids, then this thing goes away, right? But if it's periodic, you can just use this. Okay? And what you really have is 1 over n sum of e to the power I q dot rj absolute value squared, right? That's really what you have for a periodic 1D lattice. And I'm going to just assume, let's assume we are bouncing light off almost at a grazing incidence, so it's the angle. I'm not worried about the angle at this point. I'm kind of shooting it at the same axis as it's coming in as a plane wave along the atoms, and so that's how it's going to look. And RJs are now basically some integer times a naught, where you're summing over n, right? Does that make sense? This is a naught, and you're summing over, right? And that's a sum that we know how to do. So you can label it from 0 to n minus 1, for example, right? You can start from 0, and you have n minus 1. So you have basically n atoms, big N atoms now. Right? And you realize that this is basically just a geometric sum, x plus x squared plus x cubed all the way to x to the power n or n minus 1, right? It's a geometric series. Is that clear? So that's, and we know exactly what that sum is. It's basically going to look like sine. Rather, let me write it there. So what does the geometric sum look like? It looks like e to the power I q n a naught minus 1 over e to the power I q a naught minus 1. This is mod squared, sorry. Do you see what it is? It's just geometric sum. So you get that. And you can just rearrange it a little bit, take like half of this and half of that, and convert it into a sine. It's e to the power I theta minus 1. You can convert it into a sine function, right? And when you do that, essentially what you end up getting here is a sine of q n a naught. I think there might be a 2 or some I'm missing, but that's not terribly important at this point. Okay, so it's going to look something like that. Sine squared, sorry. And so you have an analytical form for the structure factor now for this particular situation. The reason I'm really plotting or trying to do this is now I want to say what will happen if you have a very large solid versus a very small crystal. Very small nanocrystal versus a big crystal. And that you can see from here. The structure factor is something like this for this situation. Now if you want to plot this, how will it look, right? That's really the question we are asking. Let me erase this. Q. When Q goes to 0, I think you can see from here what will I get when Q goes to 0. Maybe you can. I'll ask you to also look at it. But what you will get here when Q goes to 0 is actually equal to n. And that's what you're going to get. The number of atoms in the solid. You can take some, limits of this and then show that you'll get actually equal to n. And then what we can do is, instead of plotting S, we can plot mod of S, absolute value of that. Essentially what will happen is this thing is going to, and you can plot it in a log scale. If you plot it in a log scale, this will essentially drop. Okay, drop like that. It's a sinc function, really. That's what it is. The absolute value, and it kind of oscillates, and then you do it like that, and go back up again. So you get a periodic function like that. So when you plot, it's a and you can see it has to be periodic, in Q2. It's a sign here, right? So it actually also is goes periodically. And the what I wanted to get to is the height of this is related to how many atoms you have, right? So if you have 5 atoms, the height will be actually 5. If you have a 10 to the power 20, it will be 10 to the power 20. So that height. And in addition, we also know that the width of the peak, which is the full width half max, if you might, is basically, this is equal to 1 over n, the width. How sharp is that? So the height is proportional to n, and the width, the full width half max, is proportional to 1 over n. And from the width, you can say, for example, what's the size of the nanocrystal, if it's perfect. And if you have a 5 nanometer nanocrystal, which is composed of, say, 1,000 atoms, you can start looking at 1 over 1,000 here compared to a very large number of solids. So you can measure that from looking at the widths carefully. So if you have a distribution, then you will have some randomness here, some randomness there. So if you have a distribution of many nanocrystals of different sizes, I think you can hopefully see, you can start adding them all up separately. Always add the amplitudes and then take a mod square, and you can figure out more information about the solid. Is that clear? Or so those are the two main things I wanted to point out, that from the width or full width half max of any scattering measurement, you can say what is the amount of, or how many atoms are there, are they ordered, and the crystal structure and all that. So again, you see that this repeats, and from here, this will be basically 2 pi by a naught. I think you can kind of make that out as well, right? The Q space repeat is 2 pi by a naught, 2 pi by the real space repeat, right? Yeah. Any questions on this? I can just briefly pause here if you. So there are some very interesting questions you can ask, because, for example, in a solid, what if instead of one big crystal, this we had kind of very briefly mentioned, instead of one big crystal, you had many small crystals which were oriented. They were all the same crystal structure, but they were oriented in different directions, right? So that's possible. That's a polycrystalline solid. Many small crystals in a polycrystalline, right? So now when you scatter off, right, what's going to happen? Right? What will you observe now? So for a perfect crystal, you're observing spots, right? But what will you observe now? Rings, right? Yeah, that's exactly right. You'll observe rings now. And why is that? That's pretty much it. Exactly right. So you have a set of spots here, but then you can kind of now also add on top of each of these RJs a certain rotation angle, right? So if you rotate things in real space, it will also rotate in Q space, of course, right? And what will happen now is you will have, I think you can show it mathematically, but I think it's all right to just so if I had let's say a screen collecting these, let's say these were the spots, but now because there's another crystal that is rotated by a slight angle, they'll get another spot here, another spot right there, and then you kind of start getting ring. It's typically called powder diffraction, right? Powder diffraction, because you have a lot of nanocrystallines, which you call it a powder, and when you do a powder diffraction, you'll get a set of rings, and from there you can back out also. The lattice constant is very easily measured because lattice constant is still kind of separation between the rings, so you can kind of pick that out as well. So and then as we discussed, if you had a highly disordered solid, meaning it's mostly crystalline and mostly aligned, but then there are all these kind of breaks in it and grain boundaries and things like that, and there are some parts which are dislocated. One crystal here is slightly offset from here, and then all that, right? Then what you get is still the spots, but then they kind of are not very sharp. They are broadened and all that stuff. So you get broadening because of that. So whenever you have some mosaicity and defects. So we are going to talk about these things in some detail, the defects and dislocations and grain boundaries in a couple of weeks from now. Okay. Something else I wanted to mention before I move to the next topic. Any questions here?
You said something that you were at amplitude to get more information. What was that?
Say that again?
Can you say that again? You said that you could add amplitudes or something to get more information.
Oh yeah, right. So what I was saying is, if you have a polycrystalline solid, right? So you have many solids. What I was saying is, you can actually think of it as the same problem, but for each small crystal. And to get the total structure factor, you have to do this sum for one polycrystalline nanocrystal plus another, but you have to add the amplitudes. You can't add the mod squared, because this is already mod squared, right? You have to add the field first, which is the sum, and then you have to rotate it, and then take the whole mod squared, to make sure that you get the right structure factor. That's what I meant. Yeah. And from there you will recover these ones here. Is that clear? Okay, yeah. Now the last part was really what would you get if it's amorphous, and I think you realize that it's this term will go to 0. You get just one. Basically all the photons that you shoot into the solid will still get reflected, but they will all they'll be equal intensity at all points on the screen. That's what we really mean, right? So it will be a haze background in some sense. You won't see any patterns, and it's not too different from trying to, if you have used microscopes, you also know that if you are not at the right focus, if your wavelength is off or something, it looks like a haze, right? It's the same deal really. There's nothing more fancy than that. The interesting question though is, we all know that in a solid at room temperature, the atoms are not sitting still. It's actually pretty far from it. They're all vibrating. Right? They're phonons, right? And at any given snapshot, if you take a snapshot of a solid at any given time, so we may say that the atoms are perfectly periodic, but if you were to be completely accurate, yes, they are perfectly periodic at the lowest temperatures when they're not vibrating. But if you are even more accurate, you'll know that quantum mechanics even forbids that. There is a 0-point motion, because it's a harmonic oscillator. Even at 0 Kelvin, they're not perfectly ordered, right? So there's some 0-point fluctuations around them. So what does that mean? It means that these RJs and RKs, RJ minus RK, We already talked about what would happen if it's amorphous or is nanocrystalline, assuming that they are already perfectly crystalline, right? Meaning that Rj minus Rk is always equal to some integer times, or rather square is integer times. That's always the perfect, right? But we know now, what I'm trying to say now is because of the vibrations, because of lattice vibrations, actually this is, in fact, this is, to be completely accurate, it's actually never equal to, an integer times a naught square. Do you see what I mean? It's always slightly off, right? Because of the vibrations. And when you say vibrations, that is typically, it could be random. This could be going that way. This atom could be going this way. That's randomized. Thermal vibrations are randomized. Right? So how come then we still get this? That's a very interesting question, because you might ask, and then this was what when X-ray was being developed for the first time by Ewald and the Ewald sphere. I think you probably know they were developing it for the first time. Actually, they did come up with the idea theoretically first before trying the experiment. And then there was one group of theorists that said you'll never get it because of this problem. You'll always be washed out, and then you'll never get any pattern. But it still shows up, and all it does when you have these slight variations and vibrations is it lowers the intensity. That's what it really does. By how much? It lowers it typically by e to the power minus a phonon of vibration energy over kT. And that's how much it lowers. And it's called the Debye-Waller factor. I'm not deriving it. Probably a good problem for your homework or something like that. It's called the Debye-Waller factor. It just lowers it a little bit. And so as you increase the temperature of the solid, this intensity starts getting lower and lower. And if you are very careful, you can actually measure the temperature from here of the solid. So that information is there. Okay. So just to summarize again, the structure factor tells you of crystal structure. It tells you how many atoms are there, what's the polycrystal size, the height of it, the width of it, and all that. And typically, just to look at these numbers, the phonon vibration energies of most solids. For silicon, for example, it's about 60 millielectron volts, and in gallium nitride, it would be about 90 millielectron volts. These are typical optical phonon vibration energies, and in that case, at room temperature, it's not a very strong decay, is what I'm saying. But if you start heating up to a few hundred degrees C, then you see this decay. So the Debye-Waller factor. I'm not getting into all the details of if you have a BCC or a FCC or hexagonal, what particular peaks would be there, what particular peaks would be missing. That I think you have probably seen, and I'll probably put it into this assignment problem. Basically, we had all these Bravais lattices, right? And each Bravais lattice has a unique f of q, right? The f of q that we talked about. And then depending on the nature of atoms and all that, and it also has the structure factor, so we can kind of decouple those based on this sort of picture. Okay? And all spectroscopies are using this. So it's a very general idea. So what I want to do next is actually try to go and look at the process of how we are using this, for example, also during the growth of the material, not just after you have grown the crystal. During the growth, you're also using this. In the latest equipment today, we use this during the growth as well. So I'm going to give an example of this and how it lets us track, if you're growing a compound semiconductor, it lets us track the growth in situ as you're growing. So you can actually, if something goes wrong, you can correct it and all that sort of thing. So it's not just after everything is done that you measure it. So that's what So what I want to do is kind of talk a little bit about the growth now. We will discuss in greater detail, at some point later. But I think it's a good point to just discuss the growth part of it, okay, of this crystal, of crystals now, the crystal growth. So what the first technique I'm going to just talk about right now. Again, this course is really not much about techniques as far as I'm concerned, as much about fundamental ideas, but I think it's a good point to talk about one technique because it's related to the structure factor and how we use it dynamically, as we grow. So we'll look at this is actually from, I'm borrowing some stuff from chapter 11 in Rocket's book, and this is a chapter on physical vapor deposition. Physical vapor deposition of as one method of growth of semiconductor crystals, so of semiconductor heterostructures, quantum wells, dots, all that sort of stuff. Okay? And so physical and again, the technique is actually kind of the simplest thing you can imagine. You want to grow gallium arsenide. So you need gallium, you need arsenic, right? So you take gallium, put it in some ovens, and you have a substrate on which you want to deposit, and you want to basically spray paint gallium atoms on that and arsenic atoms on that. That's really what you want to do. That's basically physical vapor deposition. Why is it called physical vapor deposition? Because we'll see later on there is a chemical vapor deposition where you actually have a chemical reaction. You start with gallium with some other atoms, a chemical that has gallium, you have another chemical that has arsenic, right? And then they go to the surface and there's a chemical reaction, and what ends up, the product is gallium and arsenide, and the rest of it has another product. It's a chemical reaction. Here, there's no such reaction. You have gallium and you have arsenic. So you're physically depositing it. That's why it's called physical vapor deposition, standard name. But I want to go through in some detail right now what is the growth process and where does this picture in the growth, right? And then that's what we'll go through right now. So I think what you see right away, these are very generic observations. I mean, you really don't need me to tell you this stuff, but let's discuss it. I'll point out some of the details of this process. So typically when you are trying to grow something, this is the substrate, right? And this is the these are evaporators. There'll be multiple ones of these. And so what you really want to do is have the atoms go and deposit on the substrate. But one of the very important things is you only want the atoms, the atoms that are depositing on the surface should be only the ones that you want, not all kinds of other stuff, because they will be impurities, they will be defects, right? So if you do this in air, you right away see that air has a lot of other gases, nitrogen, oxygen, and all that sort of thing, right? And so you may be evaporating gallium from here, but then what may be depositing here is all this other stuff as well, right? Oxygen, nitrogen, and carbon, all that kind of stuff. In addition, you may be basically trying to get gallium out from here by evaporating, but I think you know that if you have a lot of atoms in the way, or molecules in the way, the gallium atoms will collide with them, right? They may not actually make it there, right? So this is the first step of any physical vapor deposition. Let's say you have a source, right? A very general idea around, right? And then the first step is you have to get the atoms out of that source, right? First step. And then you have a substrate. You have to make sure that the atoms reach the substrate. Right? Otherwise, well, if there are all these other molecules on the way, they'll collide and they'll do a random walk and maybe deposit somewhere else. So you don't want a diffusive process for the atoms. You want a ballistic process. You want to remove everything in its way, right? And make it go directly and deposit this thing here. So those are the two first steps. And let's just briefly discuss about that. And as I said earlier, I'll discuss this in great detail later. Okay, in greater detail later. I don't know how great, but yeah. Okay, so typically what you'd be doing is for some solids, you would have a crucible. It could be typically a high temperature compatible crucible. What's used is pyrolytic boron nitride, PBN is a crucible, and then you wrap around it a wire, and you pass a lot of current through it. So you're heating it. So it's a heated source, and then right at the tip of it, you will have a little opening. It could be sometimes conical. It could be kinds of shapes depending upon what you want to grow on that side, right? And what you are really doing is you have the solid, maybe at an angle, you melt it almost, and you are evaporating it. You're evaporating the atoms. And there is a dynamics of it, which tells you that if your temperature, and you'll have maybe a thermocouple connected to this end that's measuring the temperature of this crucible. Right? So if you actually make a plot of how many atoms are coming out, what's the flux of atoms that's coming out versus the temperature. You can call it the flux of atoms versus the temperature. What you'll see is it's an exponential, and this is something I think you may have seen many times. The flux of atoms that comes out because of heat is an exponential with temperature, and it goes as, well, yeah, there's a certain activation energy over K times the temperature of the heater. So this gives you a very nice, and this is actually very accurate, meaning you can take a log scale plot of it, log of the flux, and plot it as 1 over temperature, and you will get, a very nice. And then these activation energies are typically of the order of a few electron volts, 2, 5 eV, something like that. That's how much it takes. And the fluxes here will be, meaning if you want to convert into equivalent pressures, this will be of the order of 10 to the power, say, minus 7 torr, or 10 to the power minus 9. Sorry, yeah. So you can convert into pascals, something of that sort. That's the rough pressure. We are going to, as I said, we are going to look at this in greater detail later. But just how do you get atoms out? This is the way you get atoms out. Right? You heat it up, but then not all. Not all. So what you'll see is if you look at fusion cells, what will be labeled typically is if you have the temperature and the flux. Generally, it's plotted as a log of the flux. And I think in material science courses you might have seen it. These are called the vapor pressure curves for various elements: gallium, aluminum, indium. All kinds of elements have different vapor pressure curves, right? So that really defines what sort of temperatures you want to operate at. If you want, for example, as an example, in compound semiconductors, the three very important elements are aluminum, gallium, and indium, right? So if you want the same flux, typically you would need a higher temperature with aluminum than for gallium than for aluminum for the same flux. And typically this is how it's going to be, right? And it's not a very good way of looking at it, but if the heavier the element, generally you would need a little more, more temperature to get the same flux. So generally, it's not all the time. But then you know that you have a lot of refractory elements, like molybdenum is a very refractory. You can heat it to very, very high temperatures. You get nothing out of it. Vapor pressure, basically, it is kind of like out here. For them, this is not what you want. I mean, you can't get the temp. Basically, the amount of heat necessary is not enough. For example, your wires can't carry that much current, and you start melting other things. So there are other methods then that you use to get the flux out. Okay, so let me maybe look at that method. So if you have a very refractory element, what you do is you put it in a crucible, basically a boat, right? A boat made of graphite or something else. Yes, it is water-cooled copper crucible, and so you have water going in, water coming out, and there's your very hard to evaporate material sitting there, molybdenum or something like that. Okay? And now what you do is essentially you're going to have an electron gun, right? And a filament that essentially, when you apply a very large voltage, electrons just boil out of it. I mean, just like your atoms boiling out of that, here you're shooting electrons out, and you use a magnetic field, bend the electron beam, and let it hit that refractory solid. Essentially, just physically impart on it, and by the time it reaches here, you are talking about few kilovolts of energy. So the electron is very light, by the way, right? But it's carrying an energy of a few kilovolts, so it goes and basically hits it, and then it melts it now. You can reach the high temperature then, and this is the electron beam evaporator. This is an E-beam evaporator, right? So, and then you can get the flux out. Instead of getting it through melting directly, you're using an E-beam source. All right. So that's one way to get flux of atoms that are very hard to get otherwise. And basically, if you are doing some of the complex oxides, for example, titanium or molybdenum, and anything that has these refractory elements, this is a technique that's used. And then just some details. For example, this sort of source that I mentioned, this is a typical molecular beam epitaxy source. So you're going to create a molecular beam here. Right? For this, the flux is very accurate, meaning if you set it at a certain temperature, the flux will sit there for hours. It won't change. So the noise is very weak, very small. It doesn't fluctuate too much. But the E-beam, I think if you know that current has always some noise. The short noise is also because of discreteness of electron charge. There's some, and many other things. There's some fluctuation of current, right, with time, and therefore the E-beam flux actually is not very precisely controlled. It is reasonably precisely controlled, but there's some flux. If your growth is very sensitive to the flux, then you have to work very hard to control it. So how can you control it? Well, you look at what's the flux first, right? And if you can measure the flux that's coming here, somehow, let's say you do something here and you measure the flux of atoms that's impinging here, you can feed it back into the control here, right? And you can fix it. So it's a feedback loop. Right? If it's high, you lower it. And so that's what's used. Sometimes these are actually in the process of being developed now, because actually, yeah, the technique is not terribly easy, but I think it's being used now. It's because it gives you much more precision in the growth process. So let's actually look at how would one measure things, but I will. Okay, I want to point out a couple of other things. There are many other sources, not just So this would be a typical molecular beam epitaxy source. You have this PBN sort of crucible. Here's the thermocouple, all right, and then these are the wires, the heater coils going around it. So passing a lot of current through it, few amps typically, and then you're pumping a lot of energy into it. And then it melts, and then you have this. And then this is basically a flange. In order to avoid diffusive motion, what you have done is basically this is a source, but then everything inside here is under high vacuum. I forgot to say that. Okay, so you have a high vacuum. You have pumped out all the gas from there. Right? This is typically ultra high vacuum. And here's a pump. These are multiple sources, right? You have pumped out all the air from here. And typical pressures inside the chamber when you're not growing would be 10 to the power minus 11, 10 to the power minus 10 torr. It's very, very, ultra high vacuum. And in that case, what you can show is so I think the mean free path of atoms. We're going to derive these things later, okay? The mean free path of an atom is inversely proportional to the pressure. So the lower the pressure, the longer the mean free path. And typically you lower it to about minus 11 or minus 10 torr, and then your mean free path is like a meter of an atom. So if you kind of give it enough kinetic energy, it's going to keep going for more than a meter before it can even collide with a single, atom that's hovering around in the vacuum there, right? So and then it goes ballistically and just hits and all that. So you deposit. So you're basically spraying the surface with a layer of atoms, right? And then you go with arsenic and gallium and arsenic, and you start growing your crystal that way. Now what happens here is essentially some other things that are obviously here. You have to have a phase transition of molten gallium and arsenic, which are not chemically bonded, and you have to make them into a crystal. So there's a big phase transition going on here, quite a bit of thermodynamics, quite a bit of kinetics going on here. We'll cover those things as well. So this is very precisely controlled phase transition, obviously, as you can see, because you started with atoms in vacuum and you have a crystal now. So there's a phase transition somewhere there, right? So the vacuum level typically with minus 11s in very high-end MBE sort of systems, molecular beam epitaxy systems. But it's not necessary. You can actually have a lot of growths are done at minus 6 sort of 10 to the minus 6 torr pressures, and depends on what you need. Amount of precision, amount of impurity levels you are okay with, right? So the pressure, so the pumps can be of many kinds, and we will discuss those things later, okay? So cryogenic pumps, turbo pumps, all kinds of things. What I really want to discuss now is as your atoms go and deposit, rather this sort of a cell would be called a fusion cell, and the process which gives you this sort of behavior, it's a Knudsen cell or a fusion cell. But you can have other kinds. You can have, I mean, some of the earliest growths were done not using, these sort of Knudsen cells, but essentially you had a boat in which you put your material, metal or something like that, and you pass a lot of current. This is a conductive boat. You pass a lot of current through it, and then you evaporate it. Or you had a wire, and then you had your material kind of hanging like that here, and you pass a lot of current through the wire, and this thing just evaporates, right? So and it deposits everywhere. There's no directionality to these sources. I mean, obviously this one goes only upwards, not downwards, but it doesn't have this collimated behavior, that you have with the MB with this sort of effusion cells. Makes sense. So this thing will deposit everywhere on the walls of the system. And for example, when we are doing, instead of crystal growth, when you're depositing metals for contacts in a transistor or a laser, when you deposit metal, you could use a thermal evaporator. This would be basically a thermal evaporator, or you could use an E-beam evaporator. I think here also you see there is really not much directionality. It coats everywhere in some sense. Yeah. But the effusion cell actually has a very interesting directionality. Okay? And I think it's very clear why you would want directionality. Typically what you'd be doing is, if you're growing a laser, for example, you would have a wafer which is maybe 4-inch or something like that in size, 4-inch size. And this would be typically tens of 20 centimeters, I mean less than a meter. Right? And you will have gallium atoms come out, let's say, right? I think it's very clear that you only want gallium atoms to go here. I mean, there's no need for depositing all this out. It's a waste of material, right? So you can, but at the same time, you want them to be very uniform. The flux reaching here should be equal to the flux reaching there. It should be not. I think you see there's a trade-off, right? If you let it go in all directions, you are assured that it will be reasonably uniform here because it's like far away in some sense, right? If you take it very far, but then you're wasting a lot of material, right? So there's a lot of work that goes into designing, the flux, the angle at which the atoms come out, and depending upon the geometry of the crucible itself, if you have a rectangular or rather cylindrical crucible, you'll have this. If you kind of make it at an angle here, I think you can kind of physically intuitively see that it should spread out a little bit, right? Maybe, yeah. And you can calculate all these angles, of course. And then this sort of design goes into, so the amount of stuff that deposits, or the uniformity on the wafer will be something like that, what's shown here, for example. Right? And this part we'll discuss again when we talk about the growth in details. But so this really tells you that for certain geometries, for example, if you grow a laser here, you may have a little bit more gallium than here. That's really what it means. The amount of material that reaches there. There are some other elements. So we talked about elements that are easy to evaporate. For ones that are hard to evaporate, typically you'd be using an E-beam source, right? There are some elements of, actually arsenic is a good example. Arsenic, when you try to evaporate it from a crucible like this, arsenic comes in many forms. It has obviously the atomic form. You would like to have that. But it will come as a dimer, two arsenic atoms together. It will have, this is a monomer, dimer, tetramer, and all that. So you'll have all varieties of arsenic, which will be formed. It will be a cluster of arsenic atoms. Right? And typically, you want to be either monomers or maybe max dimers. You don't want the high element when you want to deposit it there. So what you do is, again, a very simple technique. It's called a cracker cell. So essentially, all that you have done is you have introduced a much longer and circuitous path for the atom to go through here. There are some other tricks that are played. You heat these things and all that. But essentially, the goal is you just filter out the heavier elements, heavier monomer, tetramers and all that, and you want only the lighter ones to get out here. So you make it a little harder for them. Effectively, essentially you're filtering out the heavier parts, and they just stay within the crucible, and the rest can go. And lots of other tricks. So, for example, there are gas sources. Did I have a picture of this? But by the way, this is all from your book, so you can please read this from the chapter. So, for example, nitrogen, that's a gas source. right? Nitrogen, we're not using solids, so instead of all this stuff, you'd have a inlet for a gas here, right? And gas comes in. If it's a molecular gas, then you have to make sure that you either break it and provide atomic species, right? So typically you'd be using your plasma or some sort of thing like that. How do you measure the fluxes? There are many ways, and I'm just giving you a sort of a laundry list almost here. If you want to measure just the thickness, what is typically used is a quartz crystal monitor, QCM, quartz crystal. So it's basically a crystal, and as you deposit stuff on it, it's even to the minutest nanometers you can measure because of reflectometry and all, and thickness variations. You can measure the so as you start depositing, you have electrodes and there's RF oscillator. Essentially, you're measuring the thickness of this. So it's a piezoelectric material, and its vibrational frequency really depends on its thickness very, very sensitively. So if you change its thickness by a nanometer, you'll pick up the frequency immediately, and then that's a quartz crystal monitor. There are many other kinds. There's be a ion gauge, so your atoms will kind of go through an electrical grid like this, but there's an anode and there's a cathode around it like that. And so as it goes through, there's a very huge voltage applied between them, and as the atom goes through, a gallium atom goes through it, the field is so large that it will strip out the electron from gallium atom, for example. Just pull out the electron, some electrons, and then it ionizes it, and the electrons go deposit on one grid. That doesn't really and the rest of the ion goes and deposits on the other, right? Immediately go there, and because there's a blip in current, right? Because now you had an extra electron and a positive charge, so there's a blip in current, and by how much change is there in the current, you amplify it, and you can measure how many atoms are going through it. So that's another way of it's called an ionization gauge for obvious reasons. It's ionizing the atoms and measuring how much atoms are there inside that region. Right? This does not typically give you the nature of the atom. It won't tell you whether it's gallium or aluminum or indium. It won't tell you that. It just tell you if you have aluminum, this is how many you have, the number. It won't tell you how many. Which ones, and then for that you need typically a mass spectrometer. This is a quadruple, so essentially, in a mass spectrometer you can get the information of what atoms to. So gallium or nitrogen or arsenic, you can measure that as well here in a mass spectrometer. And I'm not getting into all the details of how. Some very nice ones also. So there's electron-induced emission. You can also have the atoms going in. For example, if you have a gallium atom, this is very new these days. So if you have a gallium atom going in, by the way, if you come up with an idea here, you can start a company, because this measurement of fluxes is very hard generally in situ, and many new things develop. For example, now there's a technique where they are shooting a laser beam, it's narrow beam, and then they have a mirror and it comes back, or sometimes, and essentially what they're tracking is if you have an electron in gallium atom, every atom has a very unique spectral signature. Remember, we started this course that way, right? Every atom has a unique spectral signature. So if you have light go through and the photon energy exactly matches two levels, it will get absorbed, right, and get re-emitted, right? And by looking at how much stuff got absorbed here, you can figure out how many atoms there are. Because absorption coefficient will change with the number of atoms here, right, of the gas. But then you need a laser for every transition. If you want to track gallium, you need a unique wavelength laser. If you need aluminum, you need another, and so on. So you need typically what they have is multiple laser sources for each atom, atomic transition, and you can obviously pump them all into one optical fiber. And so this is kind of nice. It's very fast, but it requires a lot more work, in some sense. So these are all ways to track the fluxes before even the deposit there, right? So yeah. Okay, so there are some methods here that ion gauges, mass spectrometers, quartz crystals, and so on. Typically, the ion gauges are very difficult to, if you're growing oxides as an example. If you're growing oxide semiconductors, or complex oxides, This is rather tricky because the filaments oxidize very fast chemically in that environment at high temperatures and high oxygen flux. Therefore, this is typically not preferred in an oxide system. Typically, you would be using a quartz crystal monitor in an oxide system. But for environments where gallium arsenide or nitride systems, this is typically preferred. Okay, so and depends on many other details. Okay, so what I want to say now is connected to some of the structures. So this is while we are growing, so now you deposit gallium atoms. I have not spoken anything about thermodynamics and kinetics, but essentially I'm saying that let's say you start growing gallium nitride or gallium arsenide. Right? So you have gallium layer, let's say arsenic, gallium, arsenic, and you start growing a crystal. Right? And as far as how you're growing this, how you control alloys, what are the kinetics, thermodynamics, we'll talk about that later. Right now, the other technique I want to talk about is, in addition to measuring the thickness of what you're depositing, it's very important also to track what is growing. Are you growing a crystalline material? Are you growing amorphous material? Is it planar? Is it surface is smooth? Is it growing in dots? What are you growing? Can you say that as you are growing it, right? So for that, again, what we are going to do, because it's a crystal structure question, we're going to bounce off stuff from there, right, from the crystal, right, and see what comes out. And obviously here you see that it would be, you would like to do X-ray, for example, right, and while you're doing this, right. But I think one of the issues is, remember, this whole thing is in vacuum now, right? And it gets a little harder to have enough X-ray intensity over these very long distances and all that to have enough signal here. You can do it. So for that, for example, if you have a synchrotron source with very intense light beams, X-ray beam, then you can do that while growing. But typically what's used is this method here, where you're bouncing. So as you are growing that crystal layer by layer, you now bounce off electrons. Right? And electrons are relatively easy to create. So you have essentially a very low electron affinity metal, very low. So typically these are metal wires coated with cesium. Cesium has a very low electron affinity, very easy to, you apply a slightest voltage and electrons just want to leave. So they want to go into vacuum from the metal. They field ionize very easily. And so you create electron beam. So there's a wire here, and you're applying about 5 to 20 kilovolts of voltage across the wires here. And basically this part, the wire would be sticking inside the vacuum system, inside the growth system. Okay? And so this part is in ultra high vacuum, this is outside. So you have a little voltage. And then you apply 5 to 20 kilovolts and the electron beam comes out, and again, just like the atoms, it has nothing to collide with because it's vacuum. The mean free path is very long, right? And so it keeps going, and then it hits the substrate because that's where it's pointing. Right? That's where it's pointing, it keeps going, and it hits the substrate. Now, what you are doing really is, with these kilovolts here, how many kilovolts you apply, is you're controlling the wavelength of the electron. Right? How many kilovolts? Because I think we know that the wavelength of electron, according to de Broglie relation, is h over the momentum, and that is basically q times the voltage you apply. So that controls the wavelength of the electron, and the direction is fixed. Right? It's going at a fixed direction determined by the geometry of the source. Right? So it's incident here, and then it bounces off and diffracts. Right? And what you measure on the screen, you have a screen here, and the screen is actually also nicely designed. So it's basically a glass viewport, but the inside of it is coated with what used to be called in long time ago as scintillators. Whenever electron hits, it's a nanocrystal, it lights up, it emits green light or blue light depending upon the coating here. These are nanocrystals, so they're and these are vacuum compatible. Okay, so essentially here again you have a little crystalline or basically a powder in some sense of very small crystals, but if you hit it with an electron, it lights up. So you can really track the luminescence and the spectra, and then you start measuring your image of the structure factor as you grow it. So the diffraction beam gives you, the reason it's done at a very small angle, so typically this angle is very small, 2 degrees, 3 degrees, is this is a surface probe. It doesn't probe deep inside the crystal. So I think so it's probably clear that if you are incident at a very small angle, just go like that. So effectively, what you're really doing is this beam really penetrates hardly one or two monolayers from the surface, 1 or 2 lattice planes from the surface, and then it diffracts, and the phosphor screen is really picking up and giving you the whole S of basically the entire intensity as a function of Q. You know what we had written here. Something like that. It's giving you that as you are growing. So you can say a lot of things from here directly. You know, here are some examples. So here are real read patterns. This is what's appearing on the screen. So here's your screen. This is what's appearing on the screen as you are growing something. And here I think it was a MBE of germanium tin alloys. So that's as a particular example. But this is what you see for all kinds of compounds, you know, gallium arsenide so what you'll get is, you know, I think from here you can start looking. So as you're bouncing this off, the Fourier transform of a very good and ordered surface, a very crystalline surface, will give you again a very nice S of Q, a very high S of Q, and you'll get as you remember, you'll get very sharp, you know, very sharp peaks. This in log scale, so you see very sharp peaks, and these are the peaks that you're seeing as you are growing the. Now, that's obviously not all. What you can do is way more than this. So this is, for example, as you grow a layer, what you'll notice is it will, you know, for example, instead of a very planar structure here, so the planar structure, it's a 2D. You know, it's kind of a 2D lattice here, and the Fourier transform for 2D set of points is basically, it's also a 2D set of points, but then in the third dimension it's uniform. So you have what you call as a rod, or a reciprocal lattice rod. You can think of a 2D crystal as, you know, one crystal, one lattice plane here, and the other lattice plane is at infinity. You know, one layer here, another one is very far out. It's still periodic, but it's, you know, mathematically the other layer is very far out, right? And therefore, in the plane of the 2D, the lattice constant is indeed 2 pi by a or a naught, whatever is the distance between the atoms. But out of plane, it is 2 pi by a very large number, you know, which is, so it's like 0. So all the points are going to join together. So the reciprocal space map of a 2D sheet would be basically whatever is the reciprocal lattice point of the 2D crystal itself in the plane, but then outside of it, it's all continuous. That's what I really mean. You can think of it that way, right? And really what this construction shows is when you shoot the electron beams here, what you pick up here on the screen is wherever these planes or these reciprocal lattice rods, as you might say, intersect with those, that's where you pick up those points. That's where you really see, and those are those points. So if you, instead of a perfectly atomically smooth 2D layer, if you had some surface roughness, meaning a layer which is only partial, not all the way 2D, then what you'll see is basically it will start getting some structure. There's obviously some disorder in this plane now, so this, you know, exact line will become a little bigger in diameter, and this is what's kind of shown here. And as a result, where it intersects, instead of a very sharp point, you will get a line like a streak. This is a streak. And what he's saying is this is almost atomically smooth, but this is when you have steps, atomic steps on the surface. So you can pick that up, and these streaks are because of that. If you have very rough surface now, then I think you can kind of think through it. You will get these, you know, this sort of spots now. If you have very rough surface, it looks more like a polycrystalline material now. It's not really polycrystalline, but there's, because now electron beam has to transmit, not just reflect, but also transmission through these. So if your surface was like that, you'd get this, very sharp spots, and you will also see some of these extra lines called Kikuchi lines and all that. So we can describe that later. If your surface is mostly smooth, but it looks like there are atomic steps, you get streaks. But if your surface looks more like there is some roughness to it, then that's what you get. There is still just remember that this whole thing is still a single crystal. It's just the surface morphology is modifying the diffraction spots into these patterns now. And then I shouldn't call it polycrystalline. I think that's the wrong term. This is basically a rough surface. It's still a single crystal, but it's just a rough surface. Polycrystalline will give you circles. It will give you circles if you are polycrystalline. And then the other thing you can wait, I'm out of time. So other very important thing, which is really one of the most useful things about reed, is as you go from one atomically smooth surface to you grow another layer, but in the middle of that layer you have only grown half of the layer, let's say, right? So you go between a very sharp spot. So any growth process, you have a layer of gallium, but it's not completely done yet. So before you started, let's say you had an atomically smooth surface, you have this. But then you have covered only half of the layer with gallium, and you have this. Then you coat the whole thing, you go back here again. So it actually oscillates between the two. The intensity will oscillate. So when you measure it, the intensity of one spot, you can zoom into one spot and you measure the intensity, you'll see these oscillations. And these are reed oscillations, and obviously, as you can see, it will let you count how many monolayers you are growing as you are growing it, right? And this is obviously extremely useful and tells you the growth rate. If you want to grow a 3 nanometer well, you can basically grow 3 nanometers and stop, right? If you want to grow 8 monolayers, you grow 8 monolayers and stop, right? And so it's extremely powerful because of this particular feature. And actually, the history is very interesting because this was discovered in not too long ago, 1980s or something like that. And this lab in UK, which was very close to a train station, and they kept measuring this, and then they said, oh, it's probably because of the train and vibration of the lines. But then many times when there were no trains, it was still showing that. So they finally figured out the reason is really because of this procedure of reflection from a rough versus smooth surface. This can be done very mathematically. You can calculate all these things, but I think the intuitive picture is very clear what's going on here, right? So because of the changes between a very smooth, perfect surface versus a relatively rougher, disordered surface, you get different scattering. Right? So. Okay, so I'll actually stop here, and next class, what I did was give you the mechanics of all these things, not much science, but next class we'll start looking at a little bit more deeper into what happens here. After all this is said and done, you deposit stuff. Are you guaranteed to have growth? Not always. You have to fix, you have to control. So basically you have like 2 or 3 control parameters: the fluxes, and the temperature. That's all you control, right? I mean, there are like 3 knobs. How much gallium, how much arsenic, and what's the temperature. That's all you control. And the pressure, of course. And then within that, we'll see there's a very small window which thermodynamically and kinetically make it possible for you to grow a crystal. If you're very far away from there, you won't grow a crystal. You will have some, you won't grow a good crystalline solid. You will have something else. So that part we'll start looking at in the next class. Yeah. Okay.